Hello everyone, I'll be talking about the Cativa catalyst and its characteristics as well as its catalytic reaction. The Cativa catalyst is an iridium-based carbonyl complex used industrially for the carbonylation of methanol to acetic acid. It's usually represented as this structure shown on the right, and the central iridium atom is coordinated to two carbonyl ligands and two iodide ligands, creating a square planar arrangement that stabilizes the metal center and makes it highly effective for catalytic carbonylation. The carbonyl ligands help activate and bind carbon monoxide, while the iodide ligands assist in key steps in the catalytic cycle like oxidative addition. The catalyst drives the carbonylation of methanol to acetic acid, and the transformation is shown through a few key steps. The starting material is methanol, and under the reaction conditions, it first reacts with hydrogen iodide to form methyl iodide, which is a species that enters the catalytic cycle. The Cativa iridium complex then undergoes oxidative addition, where the methyl iodide adds to the iridium center. Next, the molecule of carbon monoxide binds to the metal and inserts into the iridium-carbon bond, forming an acetyl-iridium intermediate. After this, the acetyl group is released from the metal as acetyl iodide, which reacts with water in a separate step to form the final product, which is acetic acid, while regenerating hydrogen iodide. The turnover number of a catalyst refers to how many times a catalyst can carry out its reaction before it becomes inactive. The Cativa catalyst has an extremely high turnover number. Reports show that the iridium catalyst can perform well over 1 million turnovers, meaning a single iridium center can convert more than 1 million molecules of methyl iodide into acetyl intermediates before deactivation. This very high turnover number is possible because the iridium complex is structurally strong and does not break down easily under reaction conditions. Its strong metal ligand framework allows it to cycle repeatedly through oxidative addition, carbonyl insertion, and reductive elimination without significant degradation, to demonstrate that the catalyst has an exceptionally long lifetime. The next characteristic is catalyst activity, that's often measured using turnover frequency, which describes how many catalytic cycles occur per unit time. For the Cativa catalyst, turnover frequency values are very high, typically reported between 3,000 and 20,000 turnovers per hour, meaning that each iridium center can carry out thousands of carbonylation cycles every hour, making the process extremely efficient. The high turnover frequency is a result of how quickly the iridium complex moves through its catalytic sequence, especially the oxidative addition of methyl iodide and the insertion of carbon monoxide, both of which occur rapidly under operating conditions. The catalyst's strong ligand environment also helps stabilize key intermediates, allowing the reaction to proceed smoothly without long delays between steps. The third characteristic is one of the most important advantages of the Cativa catalyst, which is its remarkable selectivity for producing acetic acid. In industrial operation, the catalyst typically achieves greater than 99% selectivity, meaning almost all of the methanol ultimately becomes acetic acid, with very few byproducts. This high selectivity comes from the efficiency and control of the iridium catalytic cycle, with each step proceeding through well-defined pathways that minimize competing side reactions. Because the iridium catalyst strongly favors formation of the acetyl intermediate, very little carbon monoxide is lost to unwanted reactions, and very little methanol forms side products like acetaldehyde or carbon dioxide. And because of that, nearly everything that enters the system is directed towards the desired product. This high selectivity is a key reason the Cativa catalyst is very efficient. And these are my references in this slide. Thank you.